Welcome everyone. So thanks for watching. This is our 16th live stream geometry session. So today I took the problems from South Korea's final math Olympiad. So they have a few different rounds, I think, or they have like a separate one for juniors or something like that. But yeah, South Korea usually does fairly well on the IMO. So these should be some fairly good problems. Thanks for joining Arabian Math. So I'm going to start sharing my screen here. Hold on just a second. Let me find it. Here we go. Everyone see it? All right. So here's the first problem. We have an acute triangle ABC. D and E are the altitudes from B to AC and C to AB. So I'm going to draw those in. E is a reflection. Oh, I'm sorry. So first, I'm going to note this is D and E. The reflection of E with respect to AC is S. Use my reflect tool. So those two should be S and T. Oops, sorry. Make some room here. So that's S. This is T. And I will draw this segment just to kind of make it clear. So basically TAD is isosceles and EAS is isosceles. And then we draw this, let's see. P should be the reflection of E on BC. Yes, I think I mixed them up. Wait, so E, the reflection of E with respect to AC is S. Oh, BC, yeah. Let me, all right, so I'm gonna delete T. I'm gonna reflect it about BC. So it's still on the page. That is point P. All right. So basically we know BECT is cyclic, and same with AECS. So I'm going to draw that in later. The circumcircle of CST hits AC at point X, right? Let me just make a little bit of room. So I'm going to hide some of the excess stuff later. So this is X. And then we want to draw, we want to denote the center of that circle that I just drew. So O is the center of C. We want to show that XO is perpendicular to DE. All right, so I'm going to hide some of the excess stuff. All right. And I'll draw in some other segments just to make it clearer. So like BECT is a kite and AECS is a kite. And they're both 90-degree angle kites. Okay. Oh, it looks like I hid O. So if we take this circumcenter of ABC, the line connecting A to that point is perpendicular to DE. So I'm gonna, maybe I should draw in the circumcenter of ABC. Those circles look tangent. I'll check to see if they are. So I'll let P be the center of D. But basically it's a well-known fact, so I could prove it, that AP is perpendicular to DE. So maybe we could like try to show XO is parallel to AP. Are SD and T collinear? It could be. Let's see, sure looks like it. That feels like kind of a Simpson line thing. CP and, yeah, if these circles are tangent, then CP and O are going to be collinear. So I wonder if they're tangent. And they certainly look tangent, right? So yeah, we kind of want to show that those two circles are tangent. And if we can show that, then actually, yeah, if we can show the circles are tangent, that would solve the problem. Because that would mean XO is parallel to AP by a homothency, and it's a known fact that AP is perpendicular to DE. So I can prove that later when we do the steps. All right, so I'm going to delete the, so yeah, we want to show see if SD and T are collinear, but we don't know it yet, so I'm going to delete that. Whoops. All right, so how do we show these circles are tangent? So if SD and T are collinear, I wonder if it also passes through the foot of the altitude from A. I would think it would. Like I would think, yeah. So is that obvious why that's true? So angle SDA is equal to angle EDA. If we can show that SDA is 180 minus TDA, that would show it. I think it's very likely just an angle chase because TBEDC is cyclic. So I think there's a good chance that using that TBEDC as cyclic, we can do an angle chase that shows that all those points are collinear. So I'm going to draw that in. Oops. All right. And then, yeah, how do we show that these two circles are like tangent? Is SA tangent to the circle? It looks like it. No. So what would it mean for those two circles to be homothetic? Let's see. Yeah, we want to show a homothency at C takes the circumcircle of ABC to the circumcircle of CST. It feels like it shouldn't be that hard. Let's see. Does T equal SE? No. 1 second, guys. I'll be right back. All right, thanks for waiting. Extend BD to meet SC. Let's see. Okay. Yeah, it looks like it does meet it. And that's interesting. Okay. And then would that be enough to prove they're homothetic? And then also AF kind of looks like it meets at this intersection point, right? So I think that might do it if we can prove that. Let's see. Is that obvious? Well, because angle ABD we want to show is equal to angle ACS. Yeah, that's true. That's not hard to prove that BD and G are collinear, and these are collinear. And then I feel like that should make the homophogy easier to prove, because then the circles they're homothetic if GH is parallel to DF, but it is parallel because basically if you look at triangle IDF and IGH, they're homothetic with ratio 2. So that solves the problem. So there's a few things there that I mentioned that I kind of just didn't prove yet, but I'm going to prove them right now. So hold on just a sec. By an angle chase, we could show angle OCA is 90 minus B. Okay. You're saying in order to prove, I guess, what is that? I guess first we'll type it up the way I saw it, and then I'll try to see, I guess, kind of what you were thinking. So I agree we could show that by an angle chase, but what is that? Like, how is that supposed to? What part of the problem is that supposed to prove? So for now, I'm gonna delete a few of the things. Oh, that OP and C are collinear. Okay. Let me think about that. That might be a faster way to do this. Angle OCA is 90 minus B. That's an angle PCA is also 90 minus B. Okay. So trying to think how we would do that angle chase. Do you see how to carry out that angle chase? Angle OCA is 90 minus, yeah, so 90 minus XOC over 2. And then, right, do you want to like put angle XOC in terms of XSC? Is that kind of what you were thinking? Okay. I wonder if X, E, and T are collinear, just out of curiosity. Yep, that also looks true. Okay. So XOC is 180 minus XSC over 2. ASC is 90. And then what about XSA? SAX is 180 minus A. Okay, yeah. And SXC is STC, which is DTC. Of course, that's after proving those are collinear, right? Which is DBC, which is 90 minus C. Okay. So I see your way, and then I also see my way. I kind of think I'm gonna do it my way, just because I think my way is a little more conceptual and uses less angle chase, but I think that way also looks pretty interesting. All right, so what did I? Let me delete some of the extra stuff I added in. That I don't think G was a part of the original question. Sorry. I'm just gonna hide this for now. Okay, so so I'll call this H for the orthocenter. So yeah, what did I do here? Oh yeah, okay. So I'm going to delete this segment because we added it in later. Delete that circle. And I think that's everything that was in the problem initially. So, oh no, this should be H, I'm sorry. Okay, so let's write it up. So we have angle BEC equals angle BBC equals angle BPC, which is 90. So that means BEBCT is cyclic. And I've labeled P as the circumcenter of the triangle ABC, so I'll just put that up here. H be the orthocenter. Okay. So I'm going to draw on that circle. All right. So we wanted to show that S, D, and T are collinear. And not only that, so whoops. So first I'm gonna so the reflection of H over BC and AC lies on the circumcircle of ABC. That's a well-known fact. Or I'll say the reflections so I'll just write it like that. That's the circumcircle of ABC. That's a well-known fact. So basically, if I label these 2 points here, so F and G, so by symmetry, so since T is like the reflection of E, G has to be the reflection of H. So basically, A, H, and G are collinear, and B, H, and F are collinear. So I guess I'll write it out this way. So since so by symmetry we have to have, yeah, I'm just trying to think how to write this. I'll just write it like this. So by symmetry, ET is parallel to HG. So that means that A, H, and G are collinear. And then similarly, B, H, and F are collinear. And now I'm going to label this point, sorry, go. Okay, so now I'm going to show S, D, I, and T are collinear. And that is surely an angle chase because ADFS is cyclic and HDCI is cyclic and DIGT is cyclic. So we have a lot of cyclic quads there, so that should be enough to show S, D, I, and T are collinear. Maybe there's like a shortcut, like a Simpson line way showing that those are collinear. Because, yeah, because basically, I'll just do out the full proof. So we have angle ASF equals angle ADF equals angle HDC equals angle HIC equals angle EIG equals angle BTG, which is 90. So we have 3 cyclic quads there. So so basically that means ASFD, CDHI, and BIGT are cyclic. So so that means I'm not even going to draw in those circles, but basically we have if we can show angle, we want to show SD and I are collinear. If we can show angle SDF is equal to angle DIH, that would prove it, right? So angle SDF is equal to angle SAF, which is 90 minus angle AFS, which is 90 minus angle B, which is hold on, what am I doing here? Yeah, which is angle ICH, which is equal to angle IBH. So that means SD and I are collinear. What did I just do there? There we go. So SD and I are collinear. And similarly, T, I, and D are collinear. Right, this one just takes a while to write out. So, and then basically a homothency about H with ratio 2 takes triangle HDI to triangle HFG. And so DI is parallel to FG. So ST is parallel to FG. And that means those 2 circles are homothetic. And once we know that, basically, it eventually solves the problem. It just takes a while to write this out. So, so homothency about H with ratio 2 takes triangle HDI to triangle HFG. and that means DI is parallel to FG. Oh, it's too many dollar signs here. Okay. And so basically, if DI is parallel to FG, that means FS is parallel to ST, or that means TS is parallel to FG, which means that the circles are homothetic at C. So we have the circles ABC and XCT are homothetic at C. And if that's true, OP and C are collinear. And then that means that XO is parallel to AP. This means that OP and C are collinear, and also XO is parallel to AP. And it's well known that AP is perpendicular to DE. So that I've shown that on my channel a couple times before, that AO is perpendicular to DE. I'm sorry, that AP is perpendicular to DE. Yeah, I'll just say yeah, I'll just prove it out here really quickly. So let me think about how I want to do this, where I can make room. Make a little bit of room. All right. So we want to show angle, if we can show angle PAD plus angle ADE is 90, then that means AP is perpendicular to DE. So that's what I'm going to do. So I'll just say angle ADE is equal to angle ABC, which is half of angle APC, which is 90 minus angle PAC. So that means that AP is perpendicular to DE. And then once we know that, so since XO is parallel to AP, then XO is perpendicular to DE. All right, makes sense to everyone? Any questions on it? I think it took me as long to write out the proof as it did for us to solve it, or almost as long. All right, so I'm going to move on to the next one, if no one has any other questions. That was a cool one. All right, so let me see if anyone's joined. Sorry. Raffaello joined. Thanks for joining us. So we have a triangle ABC with in center I. And then we draw the end circle. and it meets BC, CA, and AB at D, E, and F. Whoops, that should be gray. There we go. Then we draw the circumcenters of IAB and IAC. So I'm going to draw those circles. All right. And they're O1 and O2. So O1 is the center of D. O2 is the center of E. And let the intersection, so then we draw the circumcircle of ABC and the line EF. So it passes through O1 and O2 by the in-center, X-center lemma. So it's kind of nice that GeoGebra just kind of showed us that, but that is the reason why. And okay, so we let EF meet the circumcircle of ABC at two other points, P and Q. All right. Prove the circumcenter of Vpq lies on O1, O2. So let's call that P. Let's call this Q. And we'll draw the segment. All right. The circumcenter of Vpq. So we're starting to overlap the problem a little bit. So let me draw. Let's just draw that just for the heck of it. Where's my circle? Here we go. All right, so let's draw the center P. So that's G. We want to show O1, G, and O2 are collinear. And I wonder if O1, O2 is parallel to EF. It certainly looks like it. I think it's easy to prove that O1, O2 is parallel to EF. I think that's just an angle chase.
Yeah, they're both perpendicular to AI.
Yeah, they're both perpendicular to AI because, yeah, by the in-center, X-center lemma, AO1, IO2 is a kite. So, yeah, both those are perpendicular to AI. So we want to show G lies on O1, O2. All right. See. How do we do this? C, F, O, and O1 are collinear. Yeah. Or I think you mean CI and O1 because O1 is the midpoint of arc AB. Yeah. All right. So what's a good way to do this? AO and IO2 is a kite. We know that. So P and Q lie on the polar of A. I don't know if that helps. But yeah, I feel like I've seen this configuration a lot where you let EF intersect the circle at 2 points. So yeah, let's see. I'm just going to draw it for the heck of it. Is G on the perpendicular bisector of BC? I don't think so. It doesn't look like it from the diagram, but let me check. No. I'll just label this point just for the heck of it. I wonder if H is the midpoint of BC. Thinking myself. When we show that circles are coaxial, that would be cool. If I could find a way to do that, I would think that would be cool. H is the midpoint of BC. So I feel like, and I drew in point H, so it wasn't there before. But these circles almost look concurrent too. Let's see. Oh no, they're not concurrent. Yeah, GeoGebra, the diagram keeps appearing and disappearing, but yeah, no, I'll undo that circle. So I wonder if, so PQ is like a radical axis of two of the circles. I wonder if it's also like on another circle. So PQ, G, PQ. There's only so many points in this figure. Yeah. All right. How do we show this circumcenter of one circle lies on the line between two other circles? So yeah, I mean, like we chose D as the point, but if we can show PQDH is cyclic, then we can instead think about H as, we can think of this as a circle through PQ and H, I guess, where H is the midpoint. So I wonder, let's see. I'm just thinking we could maybe draw the circumcircle of IDH. And it, and yeah, I keep forgetting about the parallelism, but yeah, O1, O2 is parallel to EF. So maybe we could even do something like this. Or like this, just making guesses here. So I wonder if AJ is perpendicular to BC. I don't think so. I think there's a little bit of an angle there. That's not 90 degrees. So I think I have an idea for how to prove PQDH is cyclic using projective geometry. So for now, I'm just going to assume PQDH is cyclic, and then when I write up the proof, I'll show how to do that. Is there some other point? Maybe we could get rid of P and Q altogether. So like we could say this is the circle through BH and something else. I'm not sure. This is a cool problem. The center of one circle lies on the line connecting the other two circles. So yeah, O1 and O2, they're midpoints of arcs A, B, and AC. So maybe it might help, like, to do this. So if we connect these points, J and K, then JK would be parallel to all those and pass through A. Yeah, this kind of reminds me of another video I did. So it's kind of like if we reflect I over G. Oh, does that pass through the midpoint of that arc? Ah. Okay, so I think L is like the midpoint of arc BAC. Okay, I feel like now we're getting some structure here. Okay, so I feel like we're closer now. So if we let L be the midpoint of arc BAC, then JALK is collinear. Is L also the midpoint of JK? I think, let's see, because here's my circle tool. L is the midpoint of JK. And I would guess that's maybe not that hard to prove. I'm not 100% sure, but just a gut instinct. Maybe power of a point, it looks like. Yeah, because LK times LA is L the center of KCBJ. So yes, or let me see. So, but yeah, I'm pretty sure it is. So yeah. So we have so much structure here that it just has to collapse, right? So let's see if we can. I'm just trying to think through a solid argument in my mind. Yeah, so we want to show L. How do we do this? Like if we could show IL is 2IG. So we want to show IG equals GL. How do we do that? Do we want to show I and L are both the same distance to point G? So in other words, they have the same power with respect to that circle. There's some transformation that sends L to H, JK to BC. Oh, like because JIK might be similar to BIC, right? So since L is the midpoint of JK and H is the midpoint of BC, I think that might, yeah. So L corresponds to H in the triangles JIK and BIC, if that makes sense. Yeah. And also LHD is 90 degrees, right? Because LH is perpendicular to BC by symmetry. So maybe we can leverage those two facts. Let's see. So we want to show GI equals GL. GI equals GL. So GI is equal to I, or no. I think maybe we could use Casey's theorem, actually. Let's see. Because we want the distance. I keep using Casey's theorem. I can't believe it. I don't know if you guys have seen it on some of my recent videos, but the length LG is the distance between the centers of two circles, right? Because L is the center of JBCK, and I is the incenter, and G is the center of this circle. So we want to show the distance between those two centers is the same as the distance between those two centers, right? Maybe we could just do stuff with like radii to prove it. So well, no, I think it's a little trickier than that, but yeah, we want to show the center of one circle is the midpoint of the center of two other circles. I'm thinking about how I can use Casey's theorem potentially. But to use Casey's theorem, we need to know the radical axis. Like for JBCK, we don't really know the radical axis of it with either of those two circles, so that would make it a little tricky. But yeah, to show G is the midpoint of IL, that looks like there has to be a way to show that. Why are they collinear? I'm actually not sure, to be honest. So, well, let's see. So G, oh no, if they are collinear, we do know G is the midpoint of IL because basically G lies on the perpendicular bisector of BH, and so that means it would have to be the midpoint of IL. So yeah, how do we show GI and L are collinear? Let's think. So yeah, once we know those three are collinear, that would solve the problem. See if anyone joined. Okay. What's up, guys? right, so G. I'm just thinking about it. So yeah, I was going to say the line connecting the centers of two circles is perpendicular to their radical axis, but we don't really know what that radical axis is. So I wonder if, like we know angle ILJ, it's the same as angle IHB. Maybe we could show angle GLJ is the same. It's just one thought. I01 O2L. Ah, it does kind of look like a parallelogram. Let's see. Yeah. So I think that certainly looks true. I think that's an angle chase, but I think, yeah. So yeah, that's a parallelogram. But yeah, how do we show G is the center of that parallelogram? So if we know it is a parallelogram, I mean, if it's a parallelogram, yeah, Li is equal to Gi, which we kind of knew. Yeah, we just have to figure out how. Yeah, so I'm going to delete this line between Gi and L, or hide it for now, because we don't really know that they're collinear. But the thing is, so G, I think we might be done, because G lies on the perpendicular bisector PQ. So since O1, O2 is parallel to PQ, G has to lie on the perpendicular bisector of O1, O2. And it also has to lie on the perpendicular bisector of DH. So I think, which means that I think those two facts might be enough to show that G has to be the midpoint of O1, O2, because it lies on both the perpendicular bisector of O1, O2 and the perpendicular bisector of DH. And there can only be one, and we know the center of this parallelogram is satisfies those two. So I think that solves it.
Why does it lie in the perpendicular bisector of O1, O2?
Because G lies on the perpendicular bisector of PQ. Because basically G is the center of this circle through P and Q. And so it lies on the perpendicular bisector of PQ, but PQ is parallel to O1, O2. So if you have two parallel chords in the same circle, if it lies on the perp bisector of one, then it also lies on the perp bisector of the other. So I think that should solve it. Because there's only one point that lies on the perpendicular bisector of both DH and O1, O2. Yeah. All right, so I'm going to write it up. This is another really good problem. Let's see what I should delete. We added a lot here. I don't even know if we needed everything we added. I don't even think we needed J, all this other stuff I added. But we did have to show that PQDH is cyclic, which I have a way of doing using projective geometry. I think I've shown that before on my channel, but I'm going to show it again. So let's delete that. Delete that. Yeah, do I even? I'm just going to delete just to make things cleaner. In fact, let me delete L for now because we introduced it later. Okay, so yeah, so to show PQDH is cyclic, uses projective geometry. So it's gonna, I have to let PQ meet BC at a point. So maybe I should just not draw that point and just call it, like mention it in my description of, yeah, this makes it a little tricky. So yeah, first I'll write out so by the in-center, X-center lemma, O1A equals O1I and O2A equals O2I. Actually, O1 and O2 are defined to be the circumcenter. So I don't even know if, I'll just say by the in-center, X-center lemma, O1 is the midpoint. Or I'll just say O1I and C are linear. Just because I've done this on my channel so many times. Yeah, earlier on in my channel, I probably would have written out more than this, but just because I've done it so many times, I'm just going to stick with this for now. All right. And so O1A, O2I is a kite. So that means that O1, O2 is parallel to PQ. Oops. And then, which means it's parallel to EF. But I'm just going to leave it like that for now. So I'm going to say let the circumcircle of Vpq meet BC at H. So let Vpq meet BC at H, and H turns out to be the midpoint of BC. And so my proof using projective geometry, you extend PQ to meet BC at a point X, and then you use the fact that X, B, C, and D are in harmonic conjugation, and then power of a point. I'm trying to remember, but so I know I've done this. So I'll set blur left. There we go. So I'll say let PQ meet BC at X, which I'm not going to draw because that would make this difficult. Then since AD, BE, and CF concur by Cheva, that means that X, B, C, D, and X are in harmonic conjugation. All right. So I've done this on my channel many times also, where I show those 4 points are in harmonic conjugation. And so it's a well-known fact that if H is the midpoint of BC, then it, since these are in harmonic conjugation, XB times XC is equal to XD times XH. So I'm going to write out that well-known fact. So I'll say if H prime is the midpoint of BC, then by a well-known fact, since BC, D, and X are in harmonic conjugation, then XB times XC is equal to XD times XH prime. I think I actually proved this in a previous live stream, so I'm not going to do the proof again. I'll just say that. But yeah, it's a fun thing to work out if you haven't seen it. So that means that by power of a point, we have XP times XQ is equal to XP times XC, which is XD times XH prime. So basically, so that's XP times XC, which by the fact we just said is equal to XD times XH prime. And that means that, I'll put this on a new line. That means that PQDH prime is cyclic, or PQH prime D is cyclic, which means that H prime equals H. All right. Okay, so yeah, we haven't drawn point X, but if you can do this in your head, that's the idea. I'm just gonna try to make a lot of room here. Okay. All right, so PQ, so H is the midpoint of BC. We know G lies on the perpendicular bisector of DH. Now I'm going to let L be the midpoint of arc BAC. Let me see, did I delete that? Yeah. I want to show that G, I, and L are collinear. Where's my perpendicular bisector? So that's J, I'll just call it J, why not? So let J be the midpoint of arc BAC. And of course that means JH is perpendicular to BC. I don't know if we'll even end up using that. Actually, yeah, we do want that. So so we want to show O1J, O2I is a parallelogram, and yes. So I'm just trying to think here. That's probably trying to think of the simplest way to show that. If we can show AJ is parallel to O1, O2, that would prove it, which is the same as saying AJ is parallel to EF. And that's true because AJ is perpendicular to AI and EF is perpendicular to AI, so that proves it. Prove that O1J is parallel to BO2. Yeah. There's probably a whole bunch of different ways to do it. Maybe there's trying to think if there's an even faster way that way. But yeah, let me see. I'm just going for efficiency here. I have a proof, it's just clunky. In fact, let me plug my computer in. So O1 is the midpoint of arc AB, and J is the midpoint of arc BAC. So yeah, there's so many ways to prove it. It's like overwhelming me, but yeah. So how about this? So we know arc O1B is half of arc AB, and arc JO2 is arc JC minus arc O2C, which is the same thing. So I think that's a very clean way to do it. So I'll just write it. So we have arc JO2 is arc JC minus arc O2C, which is half of, we'll just say this, half of arc BAC minus half of arc AC. which is half of arc AB, which is arc BO1. All right. Let's see if this fits on one line. It does. So that means that O1J is parallel to BO2. And then similarly, O2J is parallel to CO1, and so we have a parallelogram. So we have JO1 IO2 is a parallelogram. Parallelogram. All right. And once we know that, so G has to lie in the perpendicular bisector of BH and PQ. So that means it has to lie in the perpendicular bisector of O102. Yeah, okay. So I could say let G prime be the center of that parallelogram, and then that point lies on, yeah, there's just a couple ways to think about it. So I'll say, so G lies on the perp bisector of, yeah, so up here I said O102 is parallel. So O1, O2, and PQ have the same perp bisector. So that means that G lies on the perp bisector of O1, O2. And then we also have G lies on the perp bisector of BH. Okay. And I mean, it's easy to see that the center of that parallelogram meets those two criteria. So I'll just say that. So the center of the parallelogram JO1 IO2 satisfies these criteria. That implies G is the midpoint of O102, which solves the problem. All right, so I will move on to the next one after this. This is a cool one. Yeah, it's hard to write up, but yeah, there was a lot of stuff that went into this proof. I feel like especially that fact about when points are in harmonic conjugation. I didn't know this fact probably a couple weeks ago, but it's very useful. All right, Thanks everyone for your help on that. So here's the third problem. We have a triangle. So ABC is the smallest angle, and CAB is the largest, but they're all acute still. Okay. So something kind of like that. O is the circumcenter. So O is the center of C. And K is the reflection of O in BC. All right. My reflect object in line. Whoops. Reflect object in line. There we go. So this is K. And now we drop perpendiculars to AB and AC. All right. And those are D and E. So ADKE is cyclic. DE meets BC at P. Okay, so let's, all right, so this is point P. A circle with diameter AK, so we draw that. So that is the circle ADEK, right? Because ADK and AEK are both right angles. I feel like I recognize this faster than I used to be able to recognize stuff like this. So this is Q, and PQ cuts the perpendicular bisector of BC at S. Let's see. We want to show S. So it looks like K, well, yeah, K obviously lies on that perpendicular bisector. So we want to show, I guess another way to state this is if we let OK meet this circle at F, we want to show PQ and F are collinear. That's another way to say it. All right, so I'm gonna, sorry about that, I'm gonna delete some of the excess here. All right, let's hide some stuff. Hide. All right. We want to show PQ and F are collinear. Okay. And remember, K is the reflection of O over BC. I kind of wish it was called O prime, but they're calling it K. So if we can show, yeah, it looks like the radical axis theorem. Like maybe we want to use the radical axis theorem to show that FQ, DE, and BC are concurrent, right? So is BDEC cyclic? No. Yeah, let's see. What other cyclic quads? I want to use the radical axis theorem. Not sure. Is there some other kind of key point that I want to use? So I want to show FQ. Yeah, I'm just guessing the radical axis theorem. It just seems like it makes sense to me. but like for example, if I drew in this point, then I think DEGC would be cyclic if the problem were true. And so yeah, it's finding the right radical axis theorem to use, kind of. And yeah, these are all 90-degree angles. So, I mean, AF is perpendicular to FK, I think. Yeah. So AF is parallel to BC. Maybe Pascal's theorem. Looks like it could be a Pascal's thing. I'd rather use power of a point, but let's see. I want to show P, Q, and F are collinear. We could also show angle PFK equals angle QFK. Not sure how easy that is. Is Q on the perpendicular bisector of OF? I don't think so, but let's check. No. So yeah, let's go back to trying to use the radical axis theorem. So FQ, I need another key point. Is there a good point? OQ parallel to KE. It looks possible. I wonder though, sorry. I don't think so. No. So we have to use that K as the reflection of O over BC. We haven't used that yet. I wonder if AK is like a semedian. This is just a really random guess that I'm floating out here, but I think could AK be a semedian? So that's 30.8 degrees. No. Or wait a sec. 42.8. And yeah. Huh. Hmm. I want to do. Okay. So yeah, or we could let PQ meet the circle at a point. There's just so many different ways to phrase it. Like maybe it would be easier if I let PQ meet the circle at a point like F. Let's redefine F to be where PQ meets the circle, and then I want to show that FO and K are collinear. For that, yeah, that this is a perpendicular. Yeah, it doesn't seem like it should be that tricky, really. We need FA parallel to BC. Maybe I could prove, like, yeah. I think this might be the easiest phrasing of the problem. I think BQDP is cyclic. Ah, that's a good observation. Is Q the Miquel point of BC? So, do you mean BDQP or is BC? Oh no, of the quadrilateral. I think so. You're saying it is the Miquel point. Let's see. So first, I'm gonna. Okay. Because F lies on the circumcircle of ADE, and also, what are you saying? The Miquel point solves it, or? I'm a little confused. Q is the Miquel point. Yeah. Oh, I don't know why I thought you said F is the Miquel point, but yeah. Okay, so because it implies AF is parallel to BC. Okay. All right. So I'm going to type this up. So let F be the intersection of PQ with the circle. We'll just give it a name. Omega with diameter AK. All right. And then let me see if I can get some more room here. I want to be able to see point P. There we go. It's not bad. So I can make some more room here. Okay. And so basically, since Q is the intersection of the circumcircles of ADE and ABC, that means that Q is the Miquel point of the quadrilateral BDEC. And let me go back to the chat. And so that would mean that QECP is cyclic and BDQP is cyclic. Okay. Yeah, I wonder, is there a way we could, actually, I'm still not seeing it. So AFQ equals AEQ, which is QPC. And that means, yeah, okay. So AFQ is AEQ. Did we even use that K as the reflection of O over BC? I feel like we didn't even, I feel like K could have been any point on the perpendicular bisector of BC, right? It didn't even have to be the reflection. Is that true? Yeah, that's silly. Okay. So, I wonder if there's a way to state this without even having to refer to the Miquel point. But yeah, no, I agree. Q is the Miquel point of that quadrilateral. Let's see. So we would have angle CQP. What the heck? I'll just use the stuff about Miquel points because I've done it on my channel enough times. So Q is the Miquel point of quadrilateral BFEC. So basically, so it's the intersection of ABE, or I'm sorry, ADE, ABC, CP, whoops, CP, and BDP and BDP. So those four circles all intersect at point Q by the theory of the Miquel point. Okay. BDEC. Yeah, BDEC, you're right. All right. And so from there, we can do the angle chase that Ann Moll mentioned. So we have angle AFQ equals angle AEQ equals angle QPC. All right. And once we know that, that means AF is parallel to BC. Okay. And since AK is a diameter, that means angle AFK is 90. And that means that Fk is perpendicular to BC. And we want to show it's also the perpendicular bisector. So we showed Fk is perpendicular to BC. Is it obvious that it's the perpendicular bisector? I'm sure. Let's see. We already know OK is perpendicular to BC. Oh yeah, yeah. Silly me. So all right, so FO and K are collinear. Yeah, I mean that solves the problem. So we'll just say so F equals S, I'll say. All right, next problem. Thank you all for your help. I like how it used the Miquel point here.